Hi everyone, it's me, Carolyn, and today in this video we are going to be talking about probability distributions of continuous variables. We have already looked at what we did with a discrete variable. Remember, discrete means if you're looking at a number line, the outcomes are just dots along that um, number line. If we're looking at a continuous variable, the outcomes are going to be a continuous interval. So looking at infinitely many different outcomes that we could get. So thus, because of that, we won't be able to put it into our table form. So there's got to be something a little bit different when we have continuous variables. So first of all, what we're going to do is we're going to be using a curve that is going to give us the probabilities. And we call this curve a distribution curve. And when we looked at discrete variables, we looked at graphs and we had those little bars. Sometimes they are very similar, but here we're going to be talking about a curve. We will not be looking at the probability of a single value. Because there are so many outcomes, the probability of one single value happening is zero. It's kind of like zero, it's like one out of infinity, which is basically nothing. So if you think about it, what's the probability of the temperature being exactly 12 degrees and not 12.0000000001 or 11.9999999? So there are so many possibilities for temperatures. The probability for it to be exactly one value is very, very tiny. So we're going to be looking for probabilities on a range. So possibly like the probability that the temperature is between 12 and 13, or bigger than 12, or higher than 12, or lower than 12. So to calculate these probabilities, since we can't do it in table form, and we're going to be using this curve, the way we use this curve is, like I said before, it is called a density curve. We're going to be finding the areas under that curve over that region. So some things about these curves that we'll be seeing is similar to our probabilities in a discrete distribution. The curve is never going to be negative because our probabilities are never negative, and these probabilities will be the areas under these curves. We aren't going to be able to have negative areas. Also, the total area under this curve is going to be 1 because when we add up all our probabilities, we get the number 1. So when we have the total area, we're going to be talking about the total probability, so we will be getting 1. So the first thing we're going to do is be looking at some examples of some curves and just determining if they could represent a continuous random variable. So the things we have to check is making sure that they are non-negative, so they never dip below the x-axis. And this first one does not dip below the x-axis. I don't think any of the 3 examples I have does. Yeah. And so then the next thing we have to do is we have to make sure that the area under our curves is equal to 1. So you have to remember how to find area. So this is a rectangle. Notice we only have some area when we're between 6 and 8. So the area of a rectangle, if you remember, is like your base times your height. So the base of this rectangle is 2, and the height of this rectangle is 0.5. And if I do multiply those 2 together, I do get the area of 1. So this could represent a distribution curve or density curve for a continuous random variable. What it would represent, I'm not sure, but maybe it's some sort of machine that always, something happens and it always takes between 6 and 8 minutes for it to happen. Here is another example. Again, it does not dip below the x-axis, so all we have to do is make sure that the area under this curve is equal to 1. This is a triangle. So maybe you remember from your high school math courses or geometry courses that the area of a triangle is 1/2 your base times your height. Or some people think of it as base times height all over 2. They are equivalent to each other. And here we're going to our base. Notice we don't have any area outside of 0 to 5. So that is a base of 5. And our height is 0.4. And if I get those 3 numbers and drag out my calculator and multiply them together, I will be getting 1. So this could represent a curve that could be a representation of a density function for some sort of continuous random variable. Here is our last example to kind of check. Again, it is a rectangle, so the area is base times height. And our base, we're going from 2 to 6, we have a base of 4 times a height of 0.25. And if I do multiply those together, I do get the value of 1. So this also could represent a continuous random variable. So it could be the density curve for a random variable to get probabilities from. So now that we kind of know how we check, how do we actually use them to get those values? So we're going to start with something a little on the easier side, and we're going to look at something that's a uniform. So remembering uniform means flat. If you remember when we were in module 2 and we looked at, no, not module 2, I take that back. When we were looking at graphs and we were describing graphs and we said something was roughly uniform, I believe that's module 6. Uniform meant roughly flat across the top. So this would be a uniform situation. And so here, this is going to be the number of times it takes to process a credit application. So it takes anywhere from 6 to 8 minutes to do this. To find some probabilities, what we're going to do is find the area under that curve over that region of interest. So for example, if I'm looking at the probability from 6 to 7, I'm going to grab a highlighter, open it up here. So from 6 to 7, we're talking about this area here. Looking at that piece right there. So again, that is the shape of a rectangle or square, I'm not sure. And again, the area of a rectangle is your base times your height. So for the shaded region, our base is 1. Our height is 1/2. So we do get 0.5. So the probability that it's going to take between 6 and 7 minutes would be 1/2. And if it kind of makes sense, because we only go from 6 to 8, it is uniform, so we did half of it. I want to make now look that if we had included the 7, it is not going to change because it's still the same area. And if you think about when we're talking about discrete continuous, the area over one curve, one value, is nothing. So this will not change by adding a single value. It does not change the probability because the probability of a single value is basically nothing. Okay, so now let's go from 7.25 up to 9. So I'm going to do the shade this one in black. So 7.25 is about here. 9 is here, but we're going under our curve. So notice that from 8 to 9, we do not have any height. So there isn't going to be any area there. So we're going to be just going from 7.25 up to 9. The only area we have is from 7.25 to 8. So again, it is a rectangle whose base is 0.75. That's the distance from 7.25 to 8 is 3/4 or 0.75. And again, our height is 0.5. So I'm going to drag out my calculator to do my multiplication for me. And I get an answer of 0.375. So my probability that is going to take from 7.25 to 9 minutes is 0.375. We could have asked a question like, what's the probability it's going to take more than 8 minutes? And the answer to that would have been 0, because we know it's going to take somewhere between 6 and 8. So anything outside of that range does have a probability of 0. It's not going to happen. Okay, let's do a few more examples just so we can understand this idea. Again, we're going to do some sort of curve here. This has an area of 1/8. This has an area of 7/8. It's not that that matters. We are going to find the area from 2 until 7. So I'm going to shade that in. 2 is about here. 7, well, I don't know where 7 is. Maybe here. So we have this shaded region. Notice we have 2 rectangles, so we'll have to find the areas of both and then add them together because we want the total area under our curve from 2 until 7. So we're going to go from 2 to 3, which is a height base of 1. That has a height of 1/24. And to that, I'm going to add from 3 until 7, which is a base of 4. And that has a height of 1/8. So I'm going to kind of go vertically here and actually multiply these together. So 1/24 plus 4/8. And I will use my calculator to actually do that. So I will actually, and I'm going to leave it in fraction form. Feel free to take it to decimal form. If you're doing homework, make sure you give the answer in the form that it wants. So just kind of make sure of that. And we get 13 out of 24, because this would be 1/2, which is like 12 out of 24. So I'm going to add one more. I'm going to do another example. I'm going to steal a different highlighter. I'll do something a little darker, and we're going from 1, which is probably down here more, until 6, so which is a little less than that. I don't know if you can see that while I'm shading. Hopefully it's not bleeding through. I'll steal my other pages. Okay, again, we're going to find the areas of those rectangles. So the area of this first one, that base is from 1 to 3 this time, which is 2, times my 1/24. And then we will add from 3 to 6, which is 3, times my 1/8, which is 2 out of 24 plus 3 out of 8. And getting my calculator to help me a little bit, just because I want to make sure to leave it in fraction form, just to make it easier for you. But again, if you want to go to decimals, we get 11 out of 24. Feel free to do so. We are going to do one more example as far as with curves that look like this. And then we're going to turn to a curve that's a little bit more used. So here's another example. We have an archer that shoots at a bullseye target and measures the distance he is from the center of the target. So this measures how far away he is from the center of that target. And we want to know, what do we want to know? What is the probability that a randomly selected shot will be between 2 and 4 centimeters from that bullseye? Before I do that, I'm just going to say, do you think this guy is a good shot or a bad shot based on this probability curve? Remembering it telling you the probability of how far away from the center he is. This actually is telling you he's pretty good. First of all, he's always within 4 centimeters of the center, which is not very far. Also, most of the probabilities is close. So within 1 centimeter, we have the majority of the probabilities. So as you move away from from that center of the target, the probability of it hitting outside that is getting smaller. So he is a pretty good shot. But we want to find the probability from 2 to 4. So if you were writing this using probability statements, we would want it between 2 and 4. You could include the 2, you could include the 4, but we are looking for the area of that triangle. Now, the area of a triangle is 1/2 your base times your height. Our base is 2, and our height we have to figure out. So this is a nice, wonderful, straight line. It does go 4 units. We are going halfway. So if we're going halfway this way, it's going to go halfway this way as well. So our height is actually at, whoops, and I can't draw a very straight line, 2.5 or 0.25, I'm sorry, 0.25, which would have been halfway up. So I'm going to multiply those 3 things together, and the probability that he is at between 2 and 4 centimeters is 0.25. If I had wanted the probability from between 0 and 2, okay, I could find the area between there and there. However, remembering that the area under the curve is 1, has a total of 1, we have already done from 2 to 4. I can subtract what I got from 1 and get the area of that other region. So just realize that that idea of 1 minus a piece you've already done to get the rest is something we can do here as well. Okay, we are going to turn a little bit now and talk about a curve that is used over and over and over and over and over again in statistics for very good reason, which we'll see as we progress through this course. But it's going to be your normal curve, because most of our curves are not uniform. They're not rectangles. They're not even triangles. But most of the time we do have something that's a little bit more normal in nature. I'm going to zoom in just a little bit so we can see these a little better. Some characteristics about this normal curve, which we have seen already, is that it is symmetric. Okay, so remember, it's a nice even bell curve. It is centered around our mean, so the mean will be smack dab in the middle. And the standard deviation, which we've seen in Module 4, and we learned how to calculate that, it measures the spread. It's measuring how steep our curve is. So remember, the smaller your standard deviation, the more tightly compact your data is. So think about this as kind of a balloon. Remember, the area under our curve is 1. So we're going to be smushing that air in towards the mean. So that's going to make it go higher. So that kind of tells us how steep this curve is. I have some pictures here so you can kind of see what happens. This one is centered around -3, so it's got a mean of -3. Doesn't really look like, no, -2, sorry. And it has a standard deviation of 2, so it's a little flatter. This one here is centered at 0 with a standard deviation of 1. This has a mean of 2 with a standard deviation of 1/2 or 0.5. So you can kind of see that the smaller the standard deviation, so here they got smaller, they got steeper. Also, as the mean changed, it slid up or down on the number line. Okay. Again, here's some more pictures to show you that standard deviation. So they're all centered here around 100. This flatter one has a standard deviation of 20. This one has a standard deviation of 10. And this one has a standard deviation of 5. So just kind of giving you another picture of seeing how that standard deviation can change your curve. most of the time when I'm drawing my normal curves, they all look the same. And they're always usually a little wonky because I'm not a machine and I can't draw beautiful normal curves like the computer can. So just be aware that even though the standard deviation does change how the curve looks, sometimes when we draw them by hand, we aren't as good at getting that steepness the way it should be. Okay. I have one more curve picture for you, just to make sure you can really see um, those different pieces. Again, here's one centered at 0 with 0.4, very steep. Here's a centered at 0 with standard deviation of 1. This is centered at 0 with a standard deviation of 2.2. And then we slid it over to have a mean of -2, so it's centered at -2, and it has a standard deviation somewhere between the 0.4 and the 1, so it's not, so we have that value, which is 0.7. Okay, again, we're going to be looking at this curve. The area under our normal curves will be 1. So to find probabilities, if it's a normal situation, we'll be looking for the area from here to here. Now notice this is not a rectangle, so the area isn't base times your height. It isn't a triangle, so it's not 1/2 base times height. And it does have a lot here in the middle, and then it kind of quickly goes down to very little bit on the ends. Lucky for us, technology has been used to generate the probabilities under this curve for us. We will be using salt quite a bit to get those areas for us. Previously to technology, statisticians used tables, which some people still do use. And we then had to calculate something called a z-score. We still like to calculate z-scores because it gives us an idea of position. So one thing is that z-score thing that we have. And the formula for a z-score is you take your data value, you subtract your mean, and then you divide by your standard deviation. What this value gives us is how many standard deviations you are away from the mean. And it's kind of a way to compare yourself if from one situation to another. So maybe a test to another test and being able to compare yourself to peers. If I'm 3 standard deviations above the mean in one class and 2.5 standard deviations above in a second class, I did better on that first one. So that z-score is a way to compare apples to oranges, so to speak. We're going to end this video by just actually calculating a couple z-scores. And again, remembering the definition or the formula of a z-score is your data value, which we denote by x, minus our mean, which we use mu if we're talking about a population. If we're talking about a sample, we will use x bar. And then dividing by our standard deviation, which is sigma if we're talking about a population. If we were talking about a sample, we have the S show up there. So just kind of keep that in mind, those symbols that we use over and over and over again. You're going to want to be able to recognize when you see this symbol, we're talking about a mean or an average. When you see this symbol, we're talking about that standard deviation, which we like to use technology for, because to calculate it, we had to subtract off the mean, square all those up, add them all up, and then divide by n if we were talking about sigma, or n minus 1 if we were talking about s, and then take a square root. So it was a lot of work. But let's calculate a couple z-scores. Okay, and I just have 2 here for us. So we have a machine that cuts cork for wine bottles, and it operates in such a way that the diameter of the cork produced has a mean of 3 centimeters and a standard deviation of 0.1. We're going to find a z-score for the cork with a diameter of 2.95, and then we want to interpret this value. So again, our z-score, the formula is z-score is our data value, and our data value is the point of question, so that 2.95. We will subtract the mean. So our mean is at 3.0. And then we're going to divide by our standard deviation, which is 0.1. Now make sure you actually do the subtraction first. And we do want to keep the sign in there. So you'll notice we will get a negative value. So this turned out to be a negative 0.05 on the top divided by a 0.1, which gave me a negative 0.5. What this means is we are 0.5 standard deviations. And the negative tells me we are below the mean. So I am a half of a standard deviation below the mean. We're going to do the same thing for a cork with a diameter of 3.15. So again, we're going to be calculating this z-score. So we're taking our data value, which is our 315, minus our mean, which was a 3.0, divided by my standard deviation. So data value minus mean divided by standard deviation. So I'd get that 0.15 divided by 0.1. So this would give me a 1.5. So that means I am 1.5 standard deviations one and a half standard deviations, and because it was positive, we are going to be above the mean. Okay, and if we were looking at a different machine and we're calculating a 3.15, maybe its mean was different and its standard deviation was different. So we would have a different z-score. So we could find out who is closer to the average by looking at those standard deviations. And that's going to end this video for this section. When we come back in my next video, we're going to be looking more closely at that normal curve and trying to talk about exactly what are those probabilities. And we're going to start with something we call the empirical rule, which gives us some rough estimates as to so we can get a feeling for if I'm this far away, what's the probability or probability if I'm here to here and so forth. So we can start getting a feeling for how those probabilities shape out in our normal curve. But this ends this meeting. So I will see you guys all in the next video. Have a great day.